Hello. As you can see, we're getting a few people still joining the meeting, so I think it's best to wait a minute or two before we start the presentation. Okay, we haven't had anyone join in the last minute or so, so let's get started. First, I'd like to introduce myself. I'm Ben Sauer. I am the Director of Postgraduate Studies here at the Physics Department. And on behalf of all of the members of the department, I'd like to welcome you all to this unfortunately virtual open day. So what we'll be doing today, Aresh and I will be giving first a general introduction to the department and to the master's level courses. Then at 2:15 we'll start with more detailed presentations for our master's programs. And then at 3:15 we will start on more detailed presentations regarding the research possibilities for PhD students. So, and I hope that we have time for questions as we go along. It's a little more awkward to ask questions on Teams than it is in person. But if you want, you can, probably the best way to ask questions is to put them into the chat. And I'll try to pay attention to the chat as we go along in the meeting. And I'm sure the other presenters will as well. Okay, so as I said, this is the Physics Department Open Day. Sorry, the date's out of date on this. It's 2021, 2022. This to give you a little introduction into the physics department. Imperial Physics is one of the largest physics programs in the UK. We have something like around 900 to 1,000 undergraduates, about 200 students as taught postgraduates. So essentially the differing master's students. And again, we have about 250 to 300 PhD students, so people on postgraduate degrees. And all of that, the core of the department, of course, or the department really is its staff more than anything else. And so there are about 100 academic staff. There are about 25 research fellows these are people who have won fellowships to do full-time research in a particular area of physics. Something around 100 to 150 research associates. These are what you would colloquially call postdocs. They're people who have fixed-term jobs in order to do a particular kind of research, and then supported by something like 100 technical and admin support staff. So it's a very large department, and you'll see that in some of the things as we go through. The reason that we have a lot of different sections in this open day presentation is because the department is so big that there's a lot of stuff that's going on in the department. A very brief overview of the master's programs that we have. You'll hear more about this in just a minute. The thing to bear in mind is that we have distinct master's programs, and they have separate admissions. And so you'll see their MSc and Emrez programs. So these are 1 or 2 year programs focused on a particular area of physics. And so they're much more specialized than the undergraduate degrees that you may be used to. But I don't want to say too much more about that now because Aresh will be talking about this in a minute. I do want to say a little bit about the research that goes on in the department. This is obviously one of the great strengths of the department. It's large, and the staff here in the department do world-class research in a wide variety of areas, covering almost everything you could possibly do in physics. To make it more manageable, we've divided our research into 4 themes, and so they're called fundamental physics, condensed matter, photon science, and then space, plasma, and climate. And you can see within these research themes, there are individual research groups. For example, the fundamental physics has high energy physics as a research group, and that's essentially the particle physics experimental group. And theoretical physics, so the theory in the fundamental physics is particle physics in sort of the broadest possible terms, because that includes gravitation, string theory, and very mathematical side of theoretical physics. If you look at the other research themes, they also actually have theory components typically. You know, condensed matter consists of experimental research and condensed matter theory research. In photon science, it's probably more heavily weighted to experiment, but in the whole research activity, there are researchers on sort of atom-light interactions, and also on quantum information and fundamental quantum mechanics. So all of the research areas have theory and experiment mixed in. And I won't say more. I'll come back when I talk about the PhD possibilities in the department to say more about what goes on in the research groups. But just to give you a flavor of what the department can do. And of course, all of this research feeds into the teaching, particularly at the master's level, with the very wide variety of different master's programs and different projects within those programs. Okay, so thanks for coming, and I will stop presenting. I'll be back in a few minutes with more specific, but I'll stop for now and turn it over to Aresh to talk about the master's programs.
Thank you, Ben. Let me just share my screen. Okay, is that something everyone can see, I hope? So I'd like to introduce myself. I'm Arash Mostofi. I'm the head of Master's Education in the Department of Physics. Welcome to this virtual open day. So the department hosts 7 separate master's programs. So I'll go through one by one each of those and give you a little flavor about what they are. So there's the MSc Physics Program. This is the straight MSc Physics Program, and actually that includes 4 separate streams. So there's the straight MSc Physics, and then there's a stream in quantum dynamics, a stream in nanophotonics, and a stream called the extended research stream. And each of those has its own compulsory and core modules that you have to take to qualify for that stream, but they're all broadly under the same umbrella of the MSc in physics. They're 1 year, 12-month or 1 calendar year full-time courses with part-time options, except for the extended research stream, where you follow the standard MSc in physics for the first 9 months in year 1, and then you come back in year 2 and do a 9-month research project, hence the extended research title of that stream. This program, this MSc Physics program, is currently led by Ben, who's just been talking to you, but from next year it will be led by Steve Warren, whose picture is here, and Ben will tell you more about this program in a presentation after mine. Then we have the MSc in Optics and Photonics and the Emrez in Photonics. I put these two together. They're both led by Professor Kenny Weir, who's also going to be here to tell you more details about these programs. And this is one of the programs, actually, like all the programs that I'm going to talk about from here on in. These are programs that are embedded in research strengths of the department. So, these are programs that have arisen from within research groups because of their strength in these particular areas. So Kenny will tell you about these 2 options, MSc Optics and Photonics and Emrez Photonics, later on. Then we have the MSc Quantum Fields and Fundamental Forces, which is run by Professor Kelly Steele from the Fundamental Theory Group in the department, and the Emrez in Soft Electronic Materials, which is led by Professor Jisun Kim, who is from the Experimental Solid State Physics Group. Bill Proud, who is also here to speak to you later, leads the MSc in Security and Resilience. This you might think is a slightly unusual MSc program to be offered by a physics department, but actually it's an extremely interesting program, and Bill will tell you more about the content and how it's run in his presentation in about half an hour's time. And finally, I'd like to mention the Emrez in Machine Learning and Big Data, led by David Colling and Nicholas Wardle. This is the department's latest Emrez program. It started only this past October, and it's focused on machine learning methods and handling big data sets in physical science. So it's the latest offering from the department, and a very interesting course, and of course very, very timely in terms of the job market and the direction things are going in there. So that's an overview of the programs that we offer. So 7 programs, one of which has a number of streams, the MSc in physics. all these programs are currently undergoing, well, with the exception of the machine learning and big data, which is a new program, all the other programs are undergoing a curriculum review process for next academic year, to start next academic year. So the specific details of those programs will change a little bit from what is currently what you'll currently be able to find in the program handbooks on the web, which outline how those programs operate this year. So next year's program will be slightly different, and the details will be put on the web as and when they're ready and approved. But broadly speaking, the content of the programs and the direction of the programs will remain similar to what they are now. So the current programs do give you an indication of what these programs will look like next year. They all consist of taught modules. We have an extremely wide range of elective modules in the department, as Ben mentioned earlier. It's a really fantastic offering that the department provides. The teaching takes a variety of forms, ranging from traditional lectures and problem classes to sort of more contemporary ways of teaching, flipped classroom, the use of technology and recordings and things like that. For those programs for which it is relevant, there's also practical laboratory work. And all of these programs include a substantial research project element. Those that are Emrez's, there's more focus on the research element than in the MSCs, but nonetheless, all the programs have a substantial research element. There's plenty of support and advice available in the department once you're here. Lots of support networks. I've just listed the ones that came to my mind here, just really to say that the department is a very, very supportive environment for you to undertake and carry on your studies. Finally, sort of more practical things. If you're keen to learn more about the tuition fees, there's the link to the college's tuition fees webpage. Scholarships and loans, I've put a link there where you can find out more information. And living costs in London, there's a link there where you can find out more information. So that's all I wanted to say before we move on to the talks from the individual program directors. If there are any questions, please feel free to type them in the chat. I'll try to answer them as best as I can.
Thanks, Arash. I've kept my eye on the chat, and so far there are no questions, so I think we'll go straight into the next part where we present the individual MSc and Emrez programs. Oops. So as Arash said, I am, as well as being the director of postgraduate studies, I'm currently the director of the Msc Physics program, which has a number of different streams, which I'll run through. And also keep in mind what Arash said, that these programs are undergoing curriculum review. And so, well, I think the information that we're presenting is correct. Some of the details might actually change. So, yes. So, as an overview, the MSc in physics is broadly equivalent to the Msc qualification that you can get in the UK. It's actually got a bit more intensive research component, and some of the courses are at a bit more advanced level than you would get in a typical Msc degree, as moving from an undergraduate into the Msc, but they're very similar. And so, in fact, they share some of the courses on it. So what I'll do in this talk is I'll run through a little bit. I won't go through every detail, but I'll run through a little bit about what's in the different streams of the MSc Physics program. So the first one is just straight MSc Physics, so it's not further differentiated. And this program actually has the widest possible choice. All of the programs have a few required modules, so all of them have a mathematical techniques module, which is specific to the MSc. And that's to make sure that everyone who comes in from all over the world in this program has the mathematical background in order to do the other courses. There's a rather fundamental course called Advanced Classical Physics, ACP, which has quite a lot of foundational knowledge for physics in general, and we do require students to take that. And then there's some skills courses that we ask you to do for research computing skills and also transferable skills that are given by the graduate school here at Imperial College. But other than that, it's fairly free, and so you'll be able to take a number of options. It says level 4 here. It means actually a minimum of 4 options. They're actually what's called level 7. And so you have of all of the options in the physics department, they tend to be available to the MSc program. So you can really tailor the program to what you're interested in. Say, if you're interested in climate science, you can do that. If you're interested in I don't know, solid state physics, then you can do that. I will say, in contrast to the quantum fields course, which you'll hear about shortly, this MSc program is probably not the program to take if you're interested in theoretical particle physics. If you're interested in theoretical particle physics, you'd be much better off applying to the quantum fields MSc program, because that's much more specifically oriented towards that particular niche, theoretical particle physics. But in general, everything else in the physics department is covered by the MSc program, the general physics one. And as I said, it's a bit bigger in terms of research than a typical MSci, because it's a 12-month program rather than a 9-month program. So you do a really substantial full-time research project during the summer term. The extended research is kind of unique. It's a 2-year program for people who are really want to get much more deeply into their research topic. The first year is the same as the first 9 months of the MSc Physics. In other words, you do the background courses and you have a wide variety of options to choose from. But then instead of doing a summer project, you come back in the second year and do a full-time 9-month project with one of the research groups. And that's enough time to really do some very serious research, to really get into a particular topic. And so it's very, very good preparation for a PhD. The disadvantage, of course, it's a 2-year program rather than a 1-year program. But if you know that you're really aiming for a PhD at the best level, it's really excellent preparation for that. Sorry, I skipped. Then there are 2 other streams that are focused on research strengths in the department. There's an MSc Physics with Nanophotonics, which is broadly the same as the regular MSc, but it has compulsory courses in areas related to nanophotonics, and so you can see those in red. So the plasmonics and metamaterials, the advanced topics in nanophotonics and in imaging, which is shared with the Optics and Photonics MSc. And the key thing is that the projects are actually specifically oriented towards nanophotonics. And so if you're interested in that area, this gives you really, really good background, an in-depth background, and lets you start your project at a higher level. And then we have a similar stream in quantum dynamics. So again, it's got a variety of, it's got the same sort of background courses that the MSc has, but there are specialized lecture modules on aspects of quantum dynamics. And quantum dynamics is quantum information is part of quantum dynamics, but it's not all of quantum dynamics. And so, for example, we have a module on laser cooling and ultra-cold atomic systems, and a module on hybrid quantum systems and quantum photonics. And so, again, this if you're interested in this quantum area, this is a very good in-depth and focused stream on the particular topic. And again, the project work is dedicated to this particular area, so you're guaranteed a project in something related to that. Okay, we'll quickly run through. Oh, this is actually an old presentation because it should say 21, 22. I changed that. The entry requirements are a BSc or from the UK or the equivalent from elsewhere. And the entry is actually highly competitive, and we require a first-class degree or the equivalent from a different country. So if you're worried about that, you can get in touch with us ahead of time to find out what the equivalent of a first class would be for your particular undergraduate education. Occasionally, we allow people with a 2-1 degree if they have other aspects which of their undergraduate education or their experience, which makes us think that they would be successful on the MSc program. It's even possible to enter with a background which is not a physics background. You know, for example, in chemistry or mathematics, but we would require that there was a significant physics content. Otherwise, you wouldn't be able to handle the level of the taught modules that we have on the program. The classes, we typically take about 50 students a year from about 200 applicants. So that tells you something about the competitiveness of it. And in terms of these streams, as you could see from my presentation, the content in the beginning is fairly similar across the streams. And so it is possible to swap between the MSc programs in the beginning. I mean, once you get too specialized, you're not able to swap anymore. Just a few final notes. If you're a UK student on an MSci, it's generally, we don't advise you to switch to the MSc, mainly because the financing is different. And if you qualify for government support for the MSci, it's not necessarily true that you'll get government support for the MSc. So if you're contemplating that because you want to do the more in-depth research or more specialized research, then you should definitely talk to us ahead of time before you apply. The other thing to bear in mind is that the MSc does not provide bursaries. And so you would need to secure your own funding if you want to take the MSc. There are very, very few scholarships. There are some that are offered by Imperial, but most of them are not oriented towards MSc students. And finally, I'll just wrap up because we want to move on to the other programs. As Arash said, Professor Steve Warren will be taking over next year for the MSc in physics. The generic email is ph.msc, so that works regardless of who the director is. I'll be staying on as the director of the quantum dynamics stream, and Professor Rupert Olton is actually staying on as the nanophotonics head. So you can contact any of us if you have specific information, or you can contact the postgrad development officer in charge of this, who's Andrew Williamson. He's in the physics department and can answer all of your questions. Okay, I'll stop there. And I saw that there were some questions in the chat. So let me stop presenting and I'll have a quick look if there's anything in the chat. It looks like the questions have been answered in the chat already. So I think the best thing would be to move on. The next person is the Optics and Photonics presentation from Kenny Weir.
Yeah, good afternoon, everyone. Unless someone says otherwise, I will assume that you can hear me and see the slides that I've got on the screen. So my name's Kenny Weir. I'm going to talk to you about the MSc in Optics and Photonics and the Emrez Photonics. My title slide has this little picture down in the right-hand corner about 100 years of living science. That was actually Imperial College celebrating 100 years of its existence back in 2016. But it has lots of nice optics in it, so I quite like to keep it on the slide. So the MSc in Optics and Photonics is a course that's designed to provide the technical and professional skills in optics, which are in demand by industry and academia. That's our strapline. And it's really providing these skills and technical abilities that's a really important part of what we try to do with this program. The program itself can be traced back to postgraduate education in optics back in the 1917, but we have moved on since there. And as Irish has said, we are undergoing curriculum review. So the things I'm going to tell you about are the things you're likely to do and the types of modules that you'll follow, what they will involve in terms of the amount of time and effort, and how they all fit together. So as I say, it's a specialization, this master's, so we're looking for candidates who want to develop these specializations in optics, and it can be with a view to either a professional career in industry or academia. We're looking for students with a good BSc or MSc degree in physics or a related discipline, and like the other MSc Emrez programs, the standard ones at least, this is a 12-month MSc running from October right through to the following September. There are three main elements that make up the structure of the MSc. There's lecture courses, laboratory and projects. Lecture courses and laboratory both take place across term 1 and term 2. The project, there's a self-study, self-contained independent project in term 2, and then the main master's summer project, the research project in one of our research labs, runs for a full 4 months through from May to September. I'll say a little bit more about each of these individually, so that you will get an understanding of what you would be doing, what would be involved. So this is term 1, and in term 1 we have our foundation lecture courses, lasers, optical measurements and devices, and imaging. And these cover the topics which anyone with a master's qualification in optics and photonics should be familiar with and aware of. We have an elective module in term 1 that students can choose from as well. As I say, this is about 160 hours in total of lecture time, or equivalent of lecture time. The elective modules, again, as has been said, are under curriculum review. So these are a flavour of what we anticipate being topics that are included in our elective modules. They may move around a little bit and not have exactly these titles, but this gives you an indication of the types of areas that we will be offering modules in. A great strength of the department is its fibre laser and its ultrafast lasers activity. Historically, we have always been very strong in optical design. Our experimental solid state group working on optoelectronics, and our quantum optics and laser science group with the laser technology. And our biomedical imaging is a strength in the department as well, and we contribute to our biomedical optics module. The self-study that I mentioned, I've put up here some selections of titles of self-study projects from previous years. I'm not going to go through them all. What I wanted to just emphasize, and it kind of amplifies what Arash said a little earlier as well, is that we have a great depth of activity, research activity in the department, and a large fraction of that is in optics and photonics, which means we can offer a wide range of topics for our self-study projects, from 3D optical imaging to atmospheric phenomena, photonic crystals, fiber lasers, and a whole host of wide-ranging topics that are active in the department. Similarly with the self-study projects, developments and applications of anti-cycling lasers, some of the shortest laser pulse and the highest power pulses are produced in the Blackett laboratory. 3D fluorescence lifetime imaging, we have a very large section working on applications of microscopy and imaging techniques for biomedical applications, and so again, we have a project there. But also, as I say, I'm not going to go through all of these, but they are selected to give you an idea of the extent and range of projects that we've done. Sorry, I feel I've missed a slide. Well, that's fine. So what can students do after this? Well, positions in industry, graduates are in high demand. Optical design, data storage, imaging, laser applications, optical components. These are all examples of areas into which graduates from this MSc program have progressed. I also said they were in demand in university research, and here are some topics which candidates who have graduated from a program, the MSc Optics and Photonics, would be well qualified to go on and undertake. And I've actually chosen this list quite carefully because all of the examples that I include in this list are areas of research in our own physics department. And so some of these areas of research you may well be hearing a little bit more about when you hear about PhD opportunities later on. There is the Emrez in photonics as well. I only have one slide for that because it has quite a large overlap with the MSc. It follows all of the core activities of the MSc, the first-term foundation courses and the first-term laboratory, but then it goes on to a longer research project running from January through until September. The Emrez program is used by the Photonics Research Group, where if a candidate has not yet completed a relevant master's qualification, they'll do this Emrez in photonics before moving on to the beginning of their PhD studies in photonics. And that's all that I wanted to say about the MSc in Optics and Photonics. Sorry, I'm getting another here. MSc in Optics and Photonics. And again, I'll look to see if there's any questions, but if not, I'll hand back to Ben to tell us who's coming up next.
Yes, thanks, Kenny. Our next speaker is Jonathan Halliwell, who's going to talk about the quantum fields and fundamental forces. So, Jonathan, over to you.
Okay, thank you, Ben. Okay, now, actually, Ben, can you just tell me if you can see this, first of all?
I can see it. I think you're on an applications page. You may have to start presenting from the start. That's it.
Okay, does this look okay?
Yep, that's starting with the theory group, so that looks fine.
Okay, good. Thanks for the chance to talk to you today. So I'm Jonathan Halliwell. I'm the admissions tutor for the Quantum Fields and Fundamental Forces MSc course. This is based in the theory group in the fundamental physics section. This is what we look like. We're a large and friendly group. Now, I'm just going to tell you very briefly about the course. And we do, by the way, have a theory group open day at the end of January, the 26th, when you can meet us in person, if possible, and hear a lot more about the course. Now, the course covers 4 main areas, which are the 4 main research areas of our group. Quantum field theory, we have a number of staff members working in this area, many aspects of quantum field theory. We are very strong in string theory, in all aspects of that, cosmology and general relativity, and also my own area, the foundations of quantum mechanics, also particularly related to other approaches to quantum gravity, but quantum foundations generally. This, by the way, is a real advertising hoarding that was put up in one of the streets in the Notting Hill area of London. We had an artist in residence a few years ago who made this image of the Schrödinger equation just to get people interested in physics. Now, this is our group. As I said, a strong presence in string theory. The ones listed in italics here are now retired, but many of them still very active. Of note here, Professor Stell is the director of the Msc course. 2 of us in quantum foundations, including me, Jonathan Halliwell, just to draw attention to that again. I will be happy to receive any emails if you've got any kind of questions of the course. A number of staff members in quantum field theory, and then also cosmology and general relativity. So in terms of academic staff, we're quite a big group. We have about 15 postdocs and visitors at any one time, 30 PhD students, and around 45 to 50 MSc students. It varies from year to year, but this coming year we'll be looking to take on about 45. Now, I'll say something briefly about PhD applications, but you'll hear a lot more about this from Professor Andrew Tolley later on this afternoon. It is very competitive. We often have over 150 applications. So we're looking for someone with a very strong first in a 4-year degree program. It also helps to have an MSc course or Cambridge Part 3 or something similar. We have 3 to 4 positions a year, funding for UK students. Applications, I would, if you're interested in this, get them in as early as you can, certainly no later than the end of January. The college deadline is May, but we start processing them in January and interviewing in mid-February. Now, our MSc program is a very good preparation for a PhD program anywhere. It's certainly not necessarily a route to the PhD program here. We often take in people directly from outside, but it is nevertheless an excellent preparation for PhD studies anywhere. So it consists of looking at the theory, techniques and applications of advanced theoretical physics. There's a set of lectures spread over 2 terms, which are also often attended by our PhD students. And then in the summer, there's a 3-month dissertation project. So it's a 12-month full-time course. There is a part-time option available, but we discourage students from doing this unless absolutely essential. Students usually end up doing this for funding reasons, but if you can organize your finances, so for instance, you work for a year before you come and then do the 12-month full-time one, that's the preferred option. The issue is that it's often very hard to work arrange a work schedule around our lecture schedule. And students on the 2-year program do actually find that rather difficult. So 12 months is a much better option. Lecture courses, there are 4 compulsory ones. This is basically the core of quantum fields, particle physics, and so on. And then quite a long list of optional courses. You need to take 4 of those or more if you like. Some of them are undergraduate courses. You can take as many as 2 of those as part of the program. If you've done your degree already from Imperial, you will naturally have less choice. So some students who do the Msc program actually end up doing all of those, and also the quantum field theory course, which overlaps with the undergrad program. So that does restrict your choice, and in some cases to no choice. So keep that in mind. Fees and funding, I suggest you look at the college website for the latest tuition fees. As Ben said in the Physics MSc, there are limited opportunities for scholarships for MSc programs. There are some, again, see the college website. Many students come on scholarships from their own country. And another option also that a number of students have taken over the years is just take a few years off, get a decent job and build up some funds and then come back. You can certainly disconnect from physics for a few years and then reconnect again without any obvious difficulties there. Applications, it's all online. But it's pretty straightforward. CV, short personal statement, maybe a page or so, undergraduate transcripts, 2 references from people who know you, at least one of whom should be an academic if you're out of academia. Our entrance requirements are a first in physics or maths. If you do maths, you need to have had some background in quantum theory and relativity as well. We usually, in fact, it's not just a first in physics, we're usually looking for a pretty good first. In fact, we do have often 120 or more applications for 45 places. So we can actually keep the bar quite high. I mean, certainly someone with a good 2-1 would actually be able to manage the course, but because we have so many applications, the entrance requirements are pretty high. Applications are processed as they arrive, so do get them in soon. The strict deadline is the end of July, and we do still consider applications then and sometimes make offers. And we usually let you know within about 6 weeks. We have an open day in January where we can go into some of these things a little bit more. Just a few more additional points. Actually, Ben mentioned the BSc plus MSc route versus the MSci. So some MSci students, if you want to do a 4-year degree, you might want to do the MSci, but there is the option of doing the 3-year BSc and then the MSc on top of that. That does have some funding implications, but on the other hand, it means you actually get more out of the 4 years because the MSc is a 1-year course and the 4th year of the MSci is only 9 months. So to get a more in-depth knowledge of theoretical physics in the 4 years, the BSc plus MSc is the best option. If anyone's thinking about doing that, please do get in touch and I can discuss that with you. Okay, so that is all from me. Are there any questions?
Thanks. I haven't seen anything in the chat, so we'll just keep an eye on that and see if anything pops up. We might as well, let's move on to our next speaker. So Lisa Bushby is going to talk about the Emrez and soft electronic materials.
Can you see that and hear me?
Yes, that's okay.
So hi everyone, I am Lisa Bushby and I work with the director of the Emrez in soft electronic materials, Ji-Sung Kim, and I help put together the scientific program for this course. It is a 1-year multidisciplinary program that is focused on creating and optimizing new types of electronic materials and devices for a diverse range of real-world applications. What do we mean by soft electronic materials? Well, these are materials that are semiconducting, but not what you would traditionally recognize as semiconductors. We work on organic molecules and polymer materials, perovskites, and other organic, inorganic hybrid systems. And because of these materials, these have lots of advantages over traditional semiconductors in that they are lightweight, flexible, and they can be solution processed. And we incorporate these materials into different electronic devices in various fields like energy for photovoltaics, solar cells, batteries and sustainable fuels, bioelectronics, wearable electronics and sensors, and chiral emitters, detectors, spintronics, and neuromorphic devices. Unlike most of the courses that you will hear about today, this Emrez is interdisciplinary, and although many of the projects come from physics, we also have teaching staff and research projects from the departments of chemistry, materials, and bioengineering. And we attract students from different backgrounds, including physics. In the first term, you will experience a very intensive program of lectures from these different disciplines that will cover the fundamentals of organic and inorganic semiconductors, material synthesis and characterization, processing, and device physics and applications. During term one, you will be matched with a research project in one of these areas, and then from term two and for the rest of the year, you'll become fully integrated into one of these research groups from the Centre for Processable Electronics. This is a large community of scientists from across college, and there's I think there's nearly 40 independent research groups involved now. So we were able to offer a huge range of different projects, and many of these will be collaborative. We place a large emphasis on cohort building and transferable skills and exposure to the wider field of soft electronic materials, so that by the end of the year, you're able to engage in a constructive discussion about it with both other scientists and with a wider audience. And we do this by offering a range of transferable skills and advanced skills courses like science communication or hands-on device fabrication. We also send all of our students on a residential school, which is likely to be in the summertime, which features academic talks and student talks, and gives time for cohort building outside cohort building activities. And along with the Centre for Processable Electronics, we offer many symposia, seminars and workshops throughout the year. And there are many opportunities for you to present your work and network with leaders in the field of soft electronic materials. So if you'd like more information about it, you can visit our website or you can contact us directly. And that's all from me.
Okay, thank you, Lisa. Again, if anyone has any specific questions, feel free to put them in the chat and we'll pick up on them. For now, let's move along. Bill Proud is going to tell us about the Security and Resilience Msc.
Oh, so good afternoon, everybody, and welcome. So I'll just share my screen and let us get on to have a look at the presentation for this particular area. So the first thing to say is this is a master's degree that is hosted by the Department of Physics. It is cross-faculty, cross-disciplinary. We have strong connections to the Institute for Security, Science and Technology. The Institute is one of Imperial College London's 6 global challenge institutes, and we've got particular emphasis on geopolitical uncertainties, climate change, the cyber environment, physical threats and protection measures. And what we aim to do is design and coordinate the application of science and technology to answer these grand security challenges and into building societal resilience. Earlier this afternoon, Arash Mostafi asked a very important question: what do physicists do in this area? And the answer is a great many things. We're very much linked into looking at the 6 umbrella areas that Imperial College London has very great strengths in, which is looking at matter, materials and manufacturing, but also sensors, sources and detection systems, data processing and algorithms, biosystems, artificial intelligence, machine learning, cyber and cyber physical systems. All of these areas have very strong input from physicists in terms of critical data analysis, in terms of building sensors, designing sensors based on physics principles. We have material scientists who work on developing the materials for it, integrating the materials, making sure they work in environments, mechanical engineers, chemists, computer scientists. It's very diverse. And diversity, we've mentioned gender diversity already this afternoon, and this course is 50% male, 50% female. But also one of the great things about Imperial College London is it is the most cosmopolitan university in the UK. We have the widest range of nationalities present in significant numbers. And on this particular course as well, we're aiming at diversity of intellectual background. So we like recruiting physicists, mathematicians, we like recruiting civil engineers, mechanical engineers, computer scientists. We aim for a very wide scope. Because of this, we link to an area, an idea, a concept, and also a group called the Innovation Ecosystem. And these are a number of companies with very strong links in the area of security and resilience, science and technology. You will have come across the products from these companies in a number of environments. Smiths, for example, make most of the detection systems used in airports. DASA looks at speeding up innovation to introduce them into mitigation systems. Northrop Grumman do a whole range of environmental modeling. Airbus, of course, again thinking about transport, and Saab, again thinking about transport. There's a large number of these organizations, and these are expanding in number, and a great number of our graduates go and work within these organizations. So what is security and resilience? Well, security is basically preventing negative events occurring both to individuals, groups, and society. And resilience is recovering from those events in the most time and cost-efficient methods possible, with the aim of maximizing human survivability, firstly, maximizing societal and organizational longevity in the second instance. And these threats come from a number of sources. They can be natural, so we can think of volcanoes, eruptions, earthquakes, tsunamis. They can be accidents based around, say, chemical plants, for example. They can be issues to do with updating software in the finance industry. This can all cause disruption to the smooth functioning of society. And then there's those things that most people would immediately think of, which are deliberate criminal activity, political activity, straightforward vandalism, fake news, etc. So there is a really broad scope of areas here that can be addressed. How do we address these? Well, we divide the human world into 4 areas: people and their behavior, the physical infrastructure in which we live, physical world in terms of physical threats and their detection, and the cyber world, the Internet of Things. And we have courses which address each of those areas. So we have behavioral research methods, behavioral science and security, physical infrastructure, infrastructure and transport security. These are modules that have very strong links to forensic psychology in terms of the human behavior methods, and civil engineering in terms of infrastructure and transport security. The whole concept of smart cities. And I'm very pleased to say that London is one of the world's 3 smart cities designated so. The physical world, we're interested in things like chemical, biological, radiological, nuclear and explosive materials. So the physical threat space very much so. And also sensors, both electronic and natural, which can detect those systems, but also provide information on the well-being and status of various remote cyber physical systems that we need to ensure the production and supply of resources to our societies. The Internet of Things is huge. So much data is being generated. As part of the course, you will learn how one of the biggest security leaks people can have is through having a smart fridge, because people never update the security software or the operating system of their fridges. We also offer modules and research which covers all of these areas. Security in Context involves lectures by active practitioners. Earlier this week, for example, we had the head of the police involved in the security of Heathrow Airport and London City Airport. We have people who look at the spread of disease due to global warming. So you get a great exposure to active practitioners from industry, government and academia. You have a long research project with which you can refine those skills. We have summer projects, some of which are supported by industry. And here we have, for example, with the Atomic Weapons Establishment, a very focused program looking at magnetic imaging tomography of landmines, low visibility landlamp mines, which are present in many countries of the world. And frankly, we need to clean them up, but it requires good sensor systems and good data analysis protocols, software, etc. You can also, as you read down this list, see a large number of different organizations, including FFI Norway, where we're looking at sensors for chemical and biological systems, as in weapon systems, because some terrorist groups and some other organizations have used these actively against civilian populations. Also, organizations like Aerospace Corporation, which are looking for the stability and security of electronic systems that are purchased, that are used to build more complex systems. This is the same information in the tabular form, listing those modules, but towards the bottom there, you'll see a thing in red. There are 2 elective modules. These are modules that can be chosen from a wide range of departments within Imperial College London and allow you to develop your own personal profile in terms of what kind of areas are interesting to you. Who do we aim to recruit? Well, natural scientists and engineers, STEM, science, technology, engineering and mathematics graduates, and high-performing social scientists. It's a minimum 2-1 entry for your undergraduate degree. We are particularly interested in your personal statement. What is the thing that motivates you? We want you to come into this quite diverse, very challenging, multidimensional environment. And so we're very interested in the motivations of the individual. Now, if anybody here has a 2-2, but has relevant government or industrial experience, then we will consider your application as well. The course is available full-time, 12 months, or part-time, 24 months for those people who are employed. And we have a significant number of part-time students on this course, which adds, again, great diversity to our student body, because these are people employed in a number of public-facing organizations, and they can bring their experience to group work, their experience to the cohort. In conclusion, I'll just say, here is how to contact us. We're very keen to hear from you. We're very happy to answer questions in advance of your application, and very much we hope to be hearing from you soon. So thank you.
Okay, thank you. Once again, feel free to put questions into the chat. We shall move along to our final speaker on Emrez programs, and this is Nick Wardle, who was going to tell us about the machine learning and big data Emrez. So Nick.
Okay, so I'll just share my slides. Hopefully you can see those.
Yeah, that's looking good.
Okay, great. All right. So yeah, welcome to the last talk in this session. So I'm Nick Wardle, and I'm one of the co-directors of the new Emrez that Arash mentioned at the very start of the session. And this Emrez is all about machine learning and big data in the physical sciences. So the first slide is really to sort of give you an idea about why machine learning and big data is something to be associated with the physical sciences. So we all know that science is driven forward by data. I think we've we've seen that in the news certainly recently, that in order to really do science and progress science, we need experimentation, and often those experiments come with very large data sets. So these data sets, especially in the physical sciences, can be huge, really gigantic data sets that we're dealing with. And we know that machine learning has a massive impact on research when the large data sets are involved. So there's all sorts of subjects that we deal with in the physics department where machine learning is already making a big difference in pushing that research. So all the way from things like MRI scanning and medical imaging down to discovering new particles at the LHC at CERN. Machine learning is involved in all of these different things. So what you'll learn on this course in this Emrez is really focused on learning the tools and the techniques that are used in data-intensive research, both in science and industry. So you'll learn a lot about various tools that are used, whether or not you carry on in the academic world or you go into industry. You'll see these tools used a lot. And so, of course, we're using the latest computational tools. So take your pick for your favorite Python or Julia-based machine learning package. You'll come across it in this course. So the structure of the course is essentially 2 core modules, which are taught modules, and these go on during the first term. So these courses are statistical methods for experimental physics. So in this course, the idea is to learn the statistics behind how we do science. So you'll learn all about the ways we do hypothesis testing and how we actually use data to learn something about the natural world that we live in. And then the second course is more of a practical course where you'll learn some of these computational tools and techniques that are used in machine learning and all sorts of data analysis. So there's a couple of plots that I stole here from the course that we taught this term. So then in terms 2 and 3, so that's the first term is all about the taught modules, and then in terms 2 and 3 you'll go on to do a research project, and I'll come on to a little bit about what that is in a second. But essentially the rest of your time on this course will be engaged in research with one of the groups, applying your knowledge in machine learning to some cutting edge area of physics or associated subjects. There's also a requirement to take 2 optional modules, so that largely these can be chosen from the Physics MSc that Ben already talked about. And the idea is that you would take modules that are related to the subject that you'll be doing research on, so you can boost your knowledge in a particular area of research by taking those modules. And we've actually developed a new option for this course, which is all about using accelerated processing for big data analysis. So using GPUs and FPGAs to really boost how we can manipulate and process large data sets. So the masters, the Emrez that we put together is really research driven. So it's very much research focused. The stuff that you'll be doing, in the research project, we really want to see what you guys will end up teaching us. So the idea is really to learn to use the expertise that you'll have got in the first term, so all those techniques in statistics and machine learning, to actually make a real contribution in some of the really challenging data intensive fields of research. So I put here a number of different collaborations and groups that we work with in the department, and these cover all sorts of areas from medical imaging at the bottom here to oceanographic surveys. There's astrophysics projects, so Sharks is a survey of galaxies, and particle physics as well, like the experiments that we have at CERN. So you'll really have an opportunity to spend time working with a supervisor in one of the research groups working on these sort of challenging big data projects. So the last slide is just to show you who we are. So David and I are the 2 co-directors of this new course. You can find our email addresses on this slide. If you want to ask any questions in particular and you don't want to put them in the chat now, feel free to send us an email to learn more. All of the things like entry requirements and things like that are available on the website that you can find the link for here. But in general, it's a similar sort of entry requirement as the other courses that you've heard. So we're looking for STEM graduates with a 2-1 or higher degree, so people with mathematics and computing backgrounds. But also, if you don't have an academic degree of that level, then we'll also accept people that have been working in industry in a relevant area for several years. So do have a look at the requirements there and see if this program is something that would interest you. So that's all I had.
Okay, thank you, Nick. So on our timetable, we will start the postgraduate research part of the open day at 1:15, and it's only 10 past at the moment. So we will have a 5-minute break, and then we'll plunge into talking about PhD opportunities in the department. So I'll keep the meeting open so we can just hang on for 5 minutes.
Hi.
Hello, welcome back, or welcome if you're just joining us for the PhD section of the Open Day now. If you're in the latter group, you may not know me. I'm Ben Sauer. I'm the Director of Postgraduate Studies here in the Physics Department. And so I'm going to give a very brief introduction to the PhDs in the department, and then we'll move on to the different research groups. As I said, the department here is divided into four overall themes research, and in those themes are actually 9 different research groups. And so we'll be hearing from each of these groups today, so I'm not going to spend very much time at all speaking about them. The groups are roughly equal numbers of staff. Some are a little bit smaller or bigger than others. High energy physics is our largest group in terms of staff numbers, and that's because it's kind of unique. There are a large number of part-time staff who also work at big research labs, at CERN in particular, but also other places all over the world. But the research opportunities in all of these areas, and we'll be hearing from all of these areas today. This next slide is just a little bit of highlights from the different research groups. Again, I don't think there's much point in me speaking about these, because we'll hear much more from the group representatives later on, and they're much more knowledgeable about what's going on. I will say, again, if you've just joined us, that if you have any questions or want to know more information about a particular topic as it's going along, please use the chat on this Teams meeting. So if you put something in chat, the person who's not speaking can then reply to you and answer questions, and it's very nice for other people to be able to see the questions and the answers that come up. I did want to say just a little bit in general about postgraduate study and just the nuts and bolts about how it all works. Most PhDs last for 3.5 years. There are exceptions. Some go for 3, some go for 4. But 3.5 is very typical. And that includes the time at the end to actually sit down and write your thesis, which takes some time, of course. Funding. Funding comes from a variety of different sources for PhDs. UKRI is the overall agency of the UK government which funds research, and the different agencies of UKRI fund different aspects of research, and quite a few of our PhD students are funded one way or the other from UKRI funds. For example, there's a STFC, Science and Technology Facilities Council, maybe. They fund most, say, particle physics and astro and space physics PhDs, but the funding comes from other places as well. There are scholarships available for PhD study. There are scholarships that are internal to Imperial, which most of them are under the President's Scholarship program. And we've had one deadline for that already, but there's another deadline in January and another one at the beginning of March. So it's not too late to apply for President's scholarships. There are also external scholarships which people bring to Imperial College, and it's also possible to self-fund your PhD studies. One thing I'll say about funding is there's generally more funding available for experimental work than there is for theory work. Every case is individual, of course, but that's kind of a general observation. So you might think about that when you're deciding what field of research you're interested in here at Imperial. The reason we'll talk via groups is that the applications, when you apply for PhD study, you apply to a group. You don't apply to the department as a whole. You have to list 1 or 2 groups that you're interested in. The application procedures do vary a little bit between groups. In some of the research groups, you'll apply to the group, and the group as a whole will make a decision about who to admit for PhD study. I know the high energy physics or the experimental particle physics works that way. On the other hand, some of the other groups, you essentially apply to the individual supervisor or a collection of supervisors on a particular topic. And so in those cases, you really need to make contact with the individual supervisor before you put the application in, because you have to know not only the group where your application will go, but also go to the individual supervisor. So it's not nearly as centralized as you might have been used to from when you applied for undergraduate degrees, where you apply to a university, a particular department of a university. And so it really does pay to make contact with the groups and supervisors ahead of time. And that's particularly important if you think you have a chance of getting one of the President's scholarships, because for a President's scholarship application, you do need a supervisor to complete a part of the application along with your application. In terms of numbers, physics accepts about 60 PhD students a year funded from all these different sources I mentioned. I believe we have more than 200 applications a year. It may be more than 300. It varies a little bit. So it is competitive, but it's not insanely competitive. And so it's certainly possible if you have the right background and interests and make contact with the right group and supervisor. It's certainly not at all impossible to get a PhD position here. So let's see, there are a few questions. We have a little bit of time, so let me have a look at if there are any questions. There's a question, do I know what funding will look like for EU students with pre-settled or settled status? If you're settled status in the UK, I believe you're treated as a home student. You of course should check with that, and when you put your application in or registry at college level, we'll look at your funding status, but I believe settled status will count for home fees. Can I apply even if I've not graduated but expect to graduate? Absolutely. So we will make an offer. There's a minimum standard to be allowed to study for a PhD, which is a 2-1. And so the offer will always be conditional on that. But many of our students apply before they actually finish their degree, simply because you'll finish your degree well, you won't get your degree until June or July at the earliest, and that's far too late to apply. So many people apply now even. There's a question, if you're a British student living in Spain, can you apply for government loans? I think you better contact us directly about that. The person to contact, I'm afraid I didn't put her name on the slide, but I'll put her name in the chat. Our administrator for research postgraduates is Lolly Sanchez, and she should be able to give you some guidance on questions like that. And the preference for graduate students or students who have already finished their degree, I don't think there's really a preference. Again, it will depend on exactly which group you're applying to. Certainly, grades are important for PhD study, but also references are important, because a lot of what you do as a postgraduate student is not really exam work, which is what you're really evaluated on when you're an undergraduate. And so in particular, most supervisors really want to see a reference from a project supervisor, because that project is sort of much more like what a PhD will actually be. There's a a specific question, which I still have time to answer. Do we work with REL, or do we expect to offer combined PhD studentships? Yes, we work. Members of the department work with a great many external organizations. So REL, the Rutherford Appleton Lab, CERN. Actually, there are quite a few other ones as well. AWE springs to mind. And often there are joint studentships which are funded partially by the department and partially by the external institution. And so again, you'll need to contact the research group and a supervisor and find out what opportunities are available. But that's absolutely their opportunities with external organizations. I'll do the final question. Do we need to apply for funding after we're admitted as PhD students? No, you should put your application in. The funded studentships that are funded from the Research Council, so UKRI, they're handled by the groups, and the groups have different procedures for deciding on the funding for those who will actually get that funded position. But the group can't make that decision until they have your application. So the first step is really to get your application in, or actually the zeroth step is to make contact with the group to see that they're actually have supervisors who have an interest in what you're interested in. But then the application needs to get in, and then there's a discussion about the funding. That's typically the way it works. Again, for the President's Scholarship, when you put your application in, you should have been in contact with a potential supervisor about getting the President's application in at the same time. But for you as a student, the President's Scholarship application is basically your application for a PhD position. Okay, we're close to 3:30. I think in the interest of time, we should just move on to the individual group presentations. And so our first one is Alan Heavens from the Astro group. So I will stop presenting and I'll turn over to Alan to start things off. By the way, I'll continue to answer the chat in writing if you come up with different questions as we go along. Alan, are you here?
Yes, I am.
Great.
I don't know if it was just me, I got thrown out or something went wrong, so but I'm back. Do you hear me?
I do. I'm not sure. My connection has been flaky as well. So, but
We hear you.
Okay, thanks. Are you ready for me to start? I've only just.
Yes, you might as well get going.
Yeah. Okay. Let me share my screen. Oh, where's it gone? Here we go. Okay, so my name is Alan Heavens. I'm the head of astrophysics, and I'm pleased to have the opportunity to tell you a little bit about what we do in the group. Firstly, I just wanted to touch on the sort of science that we do. We do a mixture of theoretical work, computer simulation, data analysis, statistics, and observations, with an emphasis more on the data analysis side and the theory side, and the theory side in some areas, with a little bit of observational work. We're one of the smaller groups. We have 13 staff, 5 postdocs, and 24 students at the moment, and we have some ties with the theory group, particularly through cosmology, and with the space and atmospheric group for the local universe bits. The sort of science that we do, we have a new and very rapidly increasing group in planet formation. So we have quite a large number of people working on planet formation, mostly from a theoretical point of view, but with some observational elements as well. and also simulations of the atmospheres of the sun and other stars. So that's more of a simulation activity, more on the theoretical side, but again with observational connections. We have, going on a larger scale, we have quite a big activity in weak lensing, also known as cosmic shear, and large-scale structure, where we're trying to learn the properties of the universe and the contents of the universe and its future and so on, and the properties of dark energy and the like. We also do work on the microwave background radiation and on deep surveys looking for high redshift quasars and looking for distant objects and looking for the implications for galaxy formation theory. And we also have a group that looks at 21 centimeter radiation. This is a relatively new field, but which is burgeoning with the square kilometer array coming up, which will be a fantastic instrument for looking at the evolution of the universe, in particular at looking at how and why the universe got reionized at some point in its past. This is a whistle-stop tour, but I wanted to pause briefly and talk to you about Astro Statistics, which is a major part of what we do. We have the Imperial Center for Inference and Cosmology here, where we devise new statistical techniques for getting the most out of the data. And I thought I would just finish by giving some of the highlights of this sort of work. You'll see in the top right here, this is the spectrum of a quasar. It was the most distant quasar known when it was discovered here, using advanced statistical techniques. This was a tiny dot, one of maybe a billion in the sky, and by using sophisticated techniques, my colleagues were able to decide which small number of these objects to look at to find the highest redshift quasars, and they found it. In the bottom left here, we have highly computational Bayesian statistics techniques which have been developed here, which or by people here, which tell us about the evolution of the universe over time, and we know more about the universe from these techniques than in some ways than in any others. And in the bottom right here, you see the advantages of doing things in a sophisticated way. This is comparing what we can do using sophisticated statistical techniques in blue, compared with the traditional techniques. This is analyzing weak lensing data, and we have error bars here, which are a factor of 5 smaller than the traditional techniques, which use the same underlying data. So that's one of the themes that we try to do. We try to devise ways of analyzing data in a way which tells us more about the universe than we get with traditional methods. So that just gives you a very quick flavor of what we do in astrophysics. We'll be holding an open day if you want to get some more details on the 19th of January. And if you want more details, then please contact my colleague, Dr. Dave Clements, whose email address is there on the screen. Okay, that's it. I'll stop there. Thanks, Ben.
Okay, thank you, Alan. As I said, you can get in touch with the individuals who are giving the presentations through the chat. We're getting a few questions in through the chat, so that's good. We'll move on to our next presentation by Professor Kim Christensen from the Condensed Matter Theory Group.
Yes, can you see my screen now?
Yes, I see it, so that looks okay.
Excellent. So condensed matter physics, well, that's the study of an immense variety of solids and liquids that are found in nature, or indeed made by humans. So metals or magnets or ceramics, semiconductors, graphene, superfluids or superconductors are some of the things that we work on within condensed matter physics. Now, solids and liquids are understood in principle in the sense that the Schrödinger equation provides a grand unifying theory on the atomic scale. But one atom on its own is a very dull thing. We all know that if you've taken an atomic physics course. But if you put together a sample, a huge number of atoms, then you get emergent behavior that cannot be understood just by looking at an isolated atom's individual properties. And indeed, it is these emergent behaviors that give the world around us this enormous variety and richness that we see. So, as you can see from that description, condensed matter physics is an enormous field of study. It accounts for about 40% of all physics worldwide, and that is reflected in the number of Nobel Prizes associated with condensed matter physics. Now, in the department, so let me see. In a department, there are two research groups under condensed matter physics, condensed matter theory, where I'm the head of, and then experimental solid state. In condensed matter theory, we are about 8 members of academic staff. 3 of those are joined with the Department of Materials. So altogether, we are about 30 people in total. So what do we do? Well, we have a quite successful physics of materials group that focuses on theory and simulations of materials. You could say that in some sense, the goal is to solve Schrödinger's equations or approximations of the Schrödinger equation to predict electronic behavior at the nanoscale, structural properties at the mesoscale, and materials properties at the macro scale. Now, when we understand material, well, that also enables us to develop new materials that perform to our wish. And indeed, the condensed matter theory group is world leading within the field of metamaterials. Metamaterials are engineered materials with extraordinary ability to focus and guide light in ways that natural materials cannot. So you might have heard about the notion of a perfect plate that does not have limitations in the sharpness of the image as conventional lenses has, or the invisible cloak, where light, as you can see in the upper right corner here, where light are guided around an object such that if you are looking at it, you can't actually see it. It makes the object invisible. Now, when we have strong correlations between electrons, then new matters new phases of matter can emerge, and those we are also interested in. So superfluids or supersolids and quantum Hall systems. And recently, we all also been interested in using neural networks, using deep learning in order to solve the Schrödinger equation. So we have a collaboration with DeepMind on doing exactly that, and we can do things already now that you cannot obtain with classical approaches. However, the idea of emergence is not confined to atoms. So, for example, we also work together with medics and biologists and in social science to look at emergence in these systems where you have many interacting units. So, for example, the lower right picture here show an example of a model of fibrillation in the heart. Normally, the activation propagate in a coordinated wave, but if it becomes irregular, then you will have fibrillation in your heart. And we are trying to model it to see how and when that happens. So why would you do theoretical condensed matter physics? Well, of course, it's theoretical physics and numerical, but there's lots of links to experiments and industry or data. And in some cases, what you're actually studying might have an effect on the real world. It's a very broad area of science, of course. It uses almost everything that you have been taught, and indeed much more. So it's very possible that you can find a niche that suits you perfectly. There's a huge range of interesting questions, so there's actually room to make a difference, in the real world. Finally, you can actually make use of a diverse number of talents and abilities. So it could be theoretical, mathematical, but it could also be computational or physical insight, or indeed just organize and interpret large data. So funding and applications. So we might have one doctoral training partnership, and this is awarded to the best applicant that we get, no matter what the area of science this student want to participate in. And then, of course, we also have the President's PhD scholarship that Ben was talking about. There are 2 rounds left, so I urge you to apply quickly if you want to go into the second round. And indeed, please do contact staff members in our group in order to discuss possibilities of applying for the President's Scholarship. And then you can also look online for more detail on the topics that we are dealing with, because here I just presented them in a very macroscopic sense. And next week on Wednesday, we have an online open day where you will see staff members present more specific projects that could potentially be a PhD project. So please go online and sign up for this open day. And if you really are interested, then you can come for an in-person visit in January, Wednesday the 19th, if we are permitted to do that at that time because of the variant we have now. So please sign up for that also. You can do that after the open day next week. So finally, I will end up with asking you to join the Condensed Matter Theory group, because it's really an adventure that you will be joining in investigating things that maybe even change the world around you. So please join us.
Okay, Kim, thank you. I will say so far it will be nice if you put your contact details on the meeting chat as well. Alan's done it for Astro, so I think as we go along, if you do that, then there'll be a record for where people can find us.
I will do that. Yeah.
Thanks. Our next speaker is Ricardo Sapienza, who's going to tell us about experimental solid-state physics.
Thank you, Ben. I hope everything is shared properly.
Yep, it's looking okay.
Perfect. So hi, everyone. I'm Ricardo Sapienza. I'm deputy head of the EXS. So as Kim said, we are the experimental side of the condensed matter section. And in particular, we investigated experimentally solid-state physics, which is, as Kim said, a very broad field of physics. And in particular, we investigate the fundamental electronic, magnetic, and optical property of matter. So matter is what joins us as a group, and in particular, we also share large facilities. So you see here in the picture one of our PhD students in one of our labs, and also we share a very large and modern fabrication facility. Of course, these are nanofabrication, because these days solid state is mostly nanostructures, and we have a clean room and a nanofabrication lab where we fabricate and make devices and material that we investigate upon. So clearly, as we are experimental, we also much closer to application than other groups, and we have a big collaboration with Samsung, for example, for displays and LED devices, with IBM for quantum computations, with neuromorphic computation, with Microsoft for quantum computation in particular, and we do have spin-off that come out of our research labs. For example, the latest is about mid-infrared spectroscopy for cancer screening, and you see that we tackle a very broad range of physics. As Kim said, solid state these days is basically quantum science of matter, which encompasses many different things. And we are divided in 4 main areas of research. So we have a large activity on renewable energies and material for energy. These are materials that either can be used to absorb light, to convert into energy, like solar cells or different kinds, or can be used for storage, of both energies or batteries or magnetocalorics. This is something very important these days, and it has to come from solid state material that you can actually fabricate. We also have a research activity in soft electronics. You saw this is the joint with an Emrez in soft electronics. And these are materials that are flexible and that have advanced properties. For example, they can emit light, absorb light, be a sensor, and so on. And you can see on the top right, there's a real sketch of our fabrication facilities. Then another research line is in functional materials. These are materials that have properties that we can control, either magnetic properties or other properties. And these are done usually through nanostructures or our ability to address the nanoscale, for example, with very small tips or devices. And this is an area that is leading to understanding of magnetic effect at the nanoscale and at the same time to application, for example, for quantum computing. And then on the bottom right is another area which is more the study of light in nanostructured materials. This is nanophotonics, which has a large activity in Imperial, and we are working on the nanoscale version of this, how we can trap light in nano object, how we can make it can emit light, how we can use it for optical computation to generate new light sources, new kind of laser, and so on. And in this field, we also have a center for Plasmodium metamaterials that, as Kim says, is a field that was born here in Imperial. So this is just a very sharp, very fast glimpse of what we do. There's a very large variety of activities, and please look at our website. You will find more information about PhD programs and projects available. There is a full list of the project that we are offering right now. You can find it on the postgrad page you see here. And please come also to our open day if you're interested in January the 19th, which is joined with a condensed matter theory. And I think that's all for me. And Ben.
Okay, thank you, Ricardo.
Back to you.
Yeah. Okay. Next on our list is Ken Long talking about high energy and particle physics.
Hi, Ben. I'm just preparing to share.
Yeah.
With luck, you see.
Yes, that's working for me now. So
yeah,
that's good.
Yeah, some kind of graphic detail. So hi, I'm Ken Long, representing the HEP group at Imperial. Difficult. Well, in a way, difficult to interact online. So we'll try and show you what we do. But I can't change the slide. There we go. So what we're really trying to do is understand the nature of matter. So if you want, we want to understand nature's building blocks. Practically what we do is use accelerators around the world to search for new fundamental particles, for the forces through which they interact, and for new phenomena such as dark energy or dark matter. So the way we do this may be characterized sort of in three areas. We are active at the highest possible energy, so that means at the LHC. So we're involved in the CMS experiment, one of the big detectors. I'll show you a picture in a minute, but so this is looking at the highest energy collisions. We're looking for very rare events in the enormous quantity of data that's produced at the LHC through the LHCb experiment. The common feature of these two activities is that we're looking for phenomena which are not described by the standard model. As you'll maybe know from your courses, the standard model is a very taut and precise theory. You're able to measure things in all sorts of different regimes and relate them back to the fundamental parameters. And with the exception of the neutrino area and dark matter, the standard model really describes all the phenomena that have been observed. So we're out there seeking for new forces. Speaking of neutrinos, we have a very active program that's developing for the future. The flagship experiment at the moment is T2K, which is in Japan, taking neutrinos from the J-Park accelerator, which is around Tokyo, and the beam goes underneath the ground in Japan, pops up close to the Pacific, and that's where the detector is, underneath the mountain at the other side of Japan. So we're trying to study how neutrinos change from one flavor into another, and they do that because, or they are able to do that because they have mass, and that's how they mix. And so people are looking at those things. The holy grail there is to try and find matter-antimatter violation in the neutrino area. That would be an enormous discovery. So a couple of pictures. On the top left is the CMS collaboration in their cavern at CERN. So it's an enormous collaboration. I think the way in which you contribute is in small teams. So there's ample opportunity for originality and inventiveness in that activity. One of the events is on the right-hand side. So I think it's remarkable the degree to which people have been able to tame the high multiplicity interactions to get the physics out. Bottom left is a picture of LHCb. So you see the well, you see the parts of the detector. What we're doing there is we're looking for the B quarks, and we're trying to project back to the origin. And by looking for rare decays, we want to find these new phenomena. On the right-hand side is people cleaning the photomultipliers inside the Super Kamiokande detector, which is part of the TTK experiment. They're remarkable photographs, and if you see the thing in real life, it's a remarkable, well, it's a remarkable thing to see. Okay, so there are other ways in which we search for fundamental particles, forces, and phenomena. We're very active in the search for dark matter. In the LZ experiment, which is underneath a mountain in America. So this is a high purity, low background experiment. The technique is extremely different to the high energy colliders that I flashed on the previous slide. Everything is about reducing background. The care with which the people are choosing materials in phototubes, in the copper that goes into the material, into the vessels, the liquid xenon itself is remarkable. There are other types of particle which decay, as of course you know, and people are looking for those decays. So in particular, we're looking for processes with muons, which according to the standard model almost don't happen. So this is, if they are observed, this is a real signal for something that is not in the present theories. And in the neutrino sector, you may have heard of observations which may indicate that there are 4 or more neutrinos. That, of course, would be somebody driving a coach and horses through the standard model. We're very active in that area too, and are leading an experiment called SOLID, which is sitting 6 meters from the core of a reactor, a research reactor in Belgium. Okay, so some pictures of that. The LZ experiment, the photograph on somebody's phone is the business end of that experiment in the mine in Davis campus in South Dakota in the US. So a couple of photos there about the LZ experiment. Comet, you can see 2 of our colleagues, Yoshi Uchida and Sven, standing outside the magnet of the comet, which is going to deliver beam to the comet experiment. That's the top right. And the SOLID experiment in the reactor is at the bottom right. Okay, so developing the program into the future, the TTK experiment is going to be not replaced, but will be superseded by Hyper Kamiokande. That's in Japan. We're active in that experiment. We're also active in the June experiment, which is being built in the same mine that houses LZ in the US. This is an enormous activity. If you think of the Blackett Laboratory and then you think of instrumenting the whole of the Blackett Laboratory with a resolution of 1 centimeter or 2, that's the scale of the experiment, and we're deeply involved in the collection of the data for that. We want to understand gravity. There's an interferometry experiment which we want to build called AION, and colleagues here are leading that experiment. That's in the design phase, so to get involved in that experiment would be really at the ground floor. And then the field that I'm involved in, I think we see that new techniques are needed in order to drive the field forward in the accelerator area. So the group is part of the John Adams Institute, so you'll find that on our website. What we do is try and develop the techniques which will be used tomorrow, and we have an active program to demonstrate and to prove those techniques in smaller accelerator systems, in particular in medical systems. And we have a laser hybrid development program which should revolutionize clinical practice in particle beam therapy on the timescale of 15 to 20 years. Okay, we exploit an enormous amount of computing power. I think that often our PhD students become super competent in all forms of computing. As I mentioned, we are trying to apply our technologies in particular into clinical or biomedical applications. So keywords there would be LARA and the Center for the Clinical Application of Particles. But in that area, we're also looking at exploiting the solid technology to look for radiation in areas where it should be, so online dosimetry, but also in areas where it shouldn't be. So looking for nuclear materials that people didn't ought to have. Okay, so moving on to sort of practical details. The group is 140 physicists strong. There's a lot of engineers. We are able to build and exploit equipment. We work both in small and large collaborations. I've tried to flash those as we went through. We design, build, operate, and exploit those experiments. And I think that's a strength of the group. It's not necessarily uniform across the UK because it's the size and strength of our staff which allows us to do that. Postgraduate students are an essential part of all of our teams. And I think the key thing about joining us as a PhD student is that you will work on really challenging projects, but you also have the opportunity, as I've tried to indicate, of spending an extended period overseas in exciting places, mixing with other exciting scientists. And of course, I do realize that the COVID pandemic has reduced the degree to which we're able to do that. But that's our ambition. It's very important to make those links. We have 5 to 6 STFC funded posts per year. There are other sources of resources too, and therefore the cohort is about 10 PhD students per year. This year we have 13. I invite you to the ATP Postgraduate Open Day, which is on the 5th of January next year. Sign up is on the web, and we're going to run, or we have conceived of running 2 events, one in person, one online. We'll have to watch how COVID develops to see whether we don't, whether we have to do an online only event. And the final thing is that instead of inviting you to see our poster in the coffee room on level 8 of the Blackett Laboratory, my colleagues and I invite you to join us in a Zoom room, which is, the link is there. I think Lolly Sanchez sent you by email the link. Please drop in if you have questions. People will be very happy to talk to you, or just you want background information. Obviously, a long time in Teams or Zoom is a frustrating thing. So perhaps if you want to meet us, drop a line to the HEP admissions panel. I'll put the link at the bottom there, and we'll arrange a date to talk to you. Thank you very much.
Okay, thank you, Ken. So yeah, that if you can put that link in the chat, that's useful as well.
I'll do that right away. Mm-hmm.
I also noticed there's a question about neutrino detectors in the chat. Maybe you can answer.
Oh heavens, I can't see the chat now.
Well, maybe when you quit sharing.
I'll write it. Let me send this and then I'll answer it. Yeah.
Okay, so our next speaker is Professor Mike Damson, who's going to talk on behalf of the photon science section. So let's move on to Mike.
Oh, hi everyone. I hope you can see the presentation.
Yeah, it's showing for me.
Great, okay. So I'm talking today about the photon science section. So this is a talk about 2 groups in physics. So there are 9 groups in physics, and this is 2 of them. We're the Quantum Optics and Laser Science group, or sometimes known as QOLS, and the Photonics group, or PHOT. I'm head of Photonics. John Tish is head of QOLS. And we have been a sort of an amalgamation section for probably 50 years or so in one form or another. But we together, photons are sort of a binding aspect of what we do with light, modern optics. But there's a significant amount of work on what might be called atomic molecular physics that relates to that. So this first slide sort of shows that that there's a very broad range of work we do, from very fundamental to applied. At one end, we're looking at things from single photons and single ions, so very quite fundamental quantum stuff, to big laser systems, right through to very applied application-driven applied science there in things like science, physics at the interface with biology and medicine. So let me say a little bit about a slide for each of the groups. There is for quantum optics and laser science. So this, let's say its mission is science using lasers and investigate, utilize, control photonic and material states and processes down to the quantum level. So there's three main groupings within quals. One is called controlled quantum systems, and if you read some of the topics there, there's obviously quantum figuring very much here to do with single photons and single ions there. This is the part of the group which would be very much if you are interested in theoretical side of quantum optics and to work there. But there is work in there that's got experimental aspects to it. There's another grouping called the Center for Cold Matter, who do some quite fundamental work there, and again, but there's a lot of experimental technology there in quantum technologies there, but they're addressing some fundamental questions about quantum optics, but also things about the standard model and using very advanced quantum technologies in that area. And the third grouping within quals is called the Extreme Light Consortium, and these deal with fairly substantial laser systems that generate femtosecond and attosecond pulses, and then these pulses are then used to generate quite extreme light matter interactions to generate things like X-rays, electron generation there, and things looking like free electron laser science going on that side. And then the other group is, I say, is photonics. So photonics, there's, as this is its mission statement, is research into science underlying optical techniques and the development of novel photonic technologies for real-world applications. So though in photonics there is work going on of a very fundamental nature, the work in photonics very much is quite applied. So the laser technology in photonics is very much about looking at lasers that are very directly applicable. For instance, we're doing work to put lasers onto satellites for Earth observation, making laser systems that will apply to medicine. In biophotonics is a very big activity in photonics. So this is applications of physics at the boundary with life sciences and medicine. And in the biophotonics area there, it's a very interesting area if you want to apply your skills in physics that cut across to other areas like medicine. So in the biophotonics group, there's a very multidisciplinary interactions of teams, particularly with the Faculty of Medicine, but dealing with a lot of healthcare providers like cancer research and so on, like that. So the type of physics being done in the photonics group is quite close to application-driven science. So to finish, is that something about studentships there. So we have some EPFC DTA studentships. There are some other studentships that come up from the pharmaceutical and CRIC. We actually have, there is a studentship called the Stratigrad one there, which is on by Dr. Murray on medical mid-infrared fiber lasers, and that's done with the Faculty of Medicine and Industry as well. I'll jump to a last slide here, which is actually applied for, there's a studentship for optical quantum computation. This is done in the in the calls part of the section, and this is about developing first generation quantum computers. So you can see the range of work that's being done there. So our open day is on the 12th of January. It will be probably split between a first half photonics and second half quals. I would ask if you are interested in any of this area to sign up for that, and we'll send you more information about the details of how the day will run of that there. And again, decisions are being made about whether it will be virtual or whether we can make it live. So I'll stop there, and we can move on.
Okay, thank you, Mike. Moving along, our next speaker will be for plasma. So Jeremy Chittenden is going to tell us about the opportunities in plasma physics. And that's looking okay already.
Oh, that's great. Thank you, Ben. So, yep, my name's Jeremy Chittenden. I'm Deputy Head of the Plasma Physics Group. As you're probably aware, of course, plasma is what we normally refer to as the full state of matter. What happens if the electrons and ions become separated in your material? It's quite a complex interplay between various different bits of classical physics that determine what goes on. There's obviously a lot of electromagnetism involved, but there's also statistical physics, quantum effects, atomic effects. All of that mishmash basically gets thrown together and produces a very complex behavior. What we tend to focus upon in our group in plasma is what we call high energy density physics, which is really plasmas under extreme states of matter, the sorts of pressures and densities that you find at the center of the sun. Now, in order to achieve that, you need to obviously put a lot of energy into your material to make it very hot. And we typically do that very rapidly as well in order to keep the system confined. So this leads to us typically dealing with some of the largest pieces of physics experimental equipment that are out there. And this includes some facilities like the National Ignition Facility, which is this very large laser facility in Lawrence Livermore Laboratory. This device here, which is called Z, which is the world's largest pulsed electrical generator, a 25 million amp current source that sits at Sandia National Laboratory. And then at the other end of the scale, when we don't do things at high energy density, when instead we're looking at fusion plasmas on a larger scale, then we might look at a much larger size plasma itself. And so this is a building of the construction site for the International Tokamak reactor being built in Bordeaux in the south of France. So this is a large-scale fusion experiment. So what you can do, of course, is when you have access to these sorts of facilities, one of the principal focuses that we're interested in is fusion energy research. And we're doing it through a variety of different approaches. But when you have access to these sorts of facilities, you can also look at some of the fundamental processes of material in extreme states of matter. And that leads on to various different sort of alternative approaches or alternative uses to these objects. So some of the things we look at is this fundamental state of extreme states of matter called the high energy density physics. But this sort of fundamental state of matter, we can also observe sort of playing a role in astrophysics, in, for example, accretion disks or young stars, but also in space physics scenarios as well. So one of the things we can do with these large facilities is we can design experiments to test our understanding of these extreme states of matter in astrophysical environments as well. But we can also use them obviously for the pursuit of fusion energy, and we're doing that principally through looking at inertial confinement fusion, which is very dense states of plasma existing for short periods of time, or the other end of the spectrum is lower density, longer lived plasmas, magnetic confinement systems. But again, there are additional things one can do with these plasmas once you have access to these large-scale facilities. And one of the things we're looking at is generation of intense particle acceleration sources from these plasmas. We also look obviously at some of the intense laser interactions with matter, or what happens if you take large pulse power experiments, high current generators, and apply them to to plasmas. Now, when we look at fusion, of course, as I was saying, there are sort of two camps essentially to this. One is the large-scale volume plasmas, which are held together by magnetic fields for long periods of time. And you're probably familiar with this through the tokamak scheme, the Joint European Torus at Culham, or the Mars scheme, which is a smaller scale UK-owned system. Both of these are Culham's based at Culham Laboratory in Oxfordshire. We're involved in this front on modeling some of the plasma dynamics and also modeling some of the energy transport in those plasmas. A larger focus for the group is looking at the opposite approach, which is inertial confinement. This is a photograph of the National Ignition Facility in California. You can see they've drawn American football fields over the roof here just to show the scale of the facility. And all of this contains enormous lasers that are basically focused down onto a very small capsule, which is then heated rapidly to produce the fusion reactions. Now, this is the area that I work in, and you may have seen in the press earlier this year that there have been some fairly dramatic results coming out from these sorts of experiments. This is a plot of the energy yield on that facility as a function of the year. And you can see we're grumbling along at low energy outputs, and then all of a sudden in August this year, we had this sudden increase in energy output. And the reason for this is the first demonstration of an ignited burning plasma in the laboratory. And what I mean by ignition is that the fusion products themselves heat the plasma up and give rise to an exponential gain in the energy output. And this was widely reported in the press across a lot of sites. So this is a major milestone in being able to try and get large amounts of energy out from an inertial confinement fusion system. The other significant development that's happened in the field is not actually scientific. It's more to do with the way in which the field has been funded. And you can imagine that these huge large-scale facilities take tens of years and tens of billions of dollars of cash injection in order to construct them and to mount the experiments. What's happened in the last 2 or 3 years is that a larger number of private investors have got involved in the field. And here are just some press announcements about lots of different sources of investment just within the last few weeks that have gone into different approaches to fusion. Basically, everyone is getting the idea that fusion maybe isn't quite so far away and that there's potentially money to be made from this. Now, what that means is, from a scientific standpoint, rather than it being a two-horse race, rather than us just having these two types of approaches, which are government funded, there are now something like 35 small-scale companies or medium-scale companies around the world, all trying to get power on the grid through fusion by a variety of different approaches. So that means there's a very broad diversity of approaches now growing up as a potential way to get fusion energy. So it's quite an exciting time to be working in the field. The other thing that we can do, as I said, with these types of drivers is we can look at different plasma physics effects in fundamental sense, both in an astrophysical context, but also what we can do with them is in terms of the intensity of the fields inside the system. So this, for example, is a picture of what's called a Herbig-Haro object. It's the jet emanating from a young star. And the idea is that the material around the star is being accreted onto the surface of it, and some fraction of it is ejected in the form of these very long jets, sometimes larger than the size of the solar system for a young star. This is actually a schematic of an experiment on one of our in-house pulse plasma drivers, where we're basically trying to explore the physics of accretion disks and the physics of these jet ejections. This is a process we call laboratory astrophysics. Now, we can do that because as a group, we have a lot of experimental capability, rather more so than any other plasma physics group in the UK. And this includes, in the basement of the Blackett Laboratory, the world's largest pulse electrical generator in an academic environment. This is called Magpie. It's a 1.5 million amp current pulse generator. And we also have the UK's largest university-based laser system called Cerberus, which sits in the building next door. But these two systems are actually coupled together to allow us to do combined experiments. Also having access to those in-house experiments, but also larger scale external facilities, such as the largest direct drive laser system, which is Omega at Rochester, or the largest indirect drive laser system, which is the National Ignition Facility. This is what the target chamber of NIF looks like. The reason why everyone is wearing red suits here is this is actually a shot from Star Trek Into Darkness, the movie, where they borrowed the National Ignition Facility because it looks a bit like the engine room of Starship Enterprise. But one of the things we find is when we couple huge amounts of laser energy into a plasma, what we typically tend to do, if we overcook it, if we put too much intensity in, instead of not generating a nice hot plasma, we tend to generate very large amounts of fast particles, energetic particles. And that's because the electric fields associated with the lasers are huge. And this actually leads to different sets of applications. For example, we can generate very high energy fluxes of electrons from a tiny amount of plasma if we hit it with very intense laser light. So this is a potential way to generate what we would call a tabletop particle accelerator. Admittedly, that table has got a very expensive laser on top of it, but basically it makes a compact way of trying to generate multi-MeV or even gigavolt sources of particles. And this can be used for all sorts of applications, not just fundamental science, but also medical radiotherapy as well. So that's a very brief run through of the sorts of things that we do. To find out more detail, please come along to our open day, which will be on January the 14th. Again, we will try to do this in person, but it may go online. We'll let you know later on, and I'll put some more details in the chat in a moment.
Thanks, Jeremy. We'll move right along. Our next speaker is for Space and Atmospheric. It's Helen Ridley. So over to you, Helen.
Hello everyone. I'm going to try and share my slides. Let's just put us in presentation mode. Hopefully. Okay, how's that working?
Yes, it's showing, but it's not showing in full screen yet.
Okay,
but I don't know.
I can fiddle this around a little bit. How's that? Any better?
Well, it's in PowerPoint, but it's actually okay. I think people can read it.
Okay, well, I'll just use it in PowerPoint, and hopefully we'll flip forward. If I do that, you get to the next slide.
That doesn't go to the next slide, so there is
Okay, let's try and sort this out. It's normally fine, so this is slightly annoying.
That's it.
That's it now?
Yeah, that's better.
Okay, so sorry about that, slight hiatus. Hello, everybody. My name's Helen Ridley, as Ben said, and I'm the Deputy Head of Group for the Space and Atmospheric Physics Group. I want to hint that there's also an oceanic part of the group too. It doesn't quite work as such a nice acronym. So our group basically researches the natural environment, the physics that controls our natural environment, and we go from a wide range of scales, right from the bottom of the ocean all the way through to the edge of our solar system and actually beyond. And we use a wide variety of tools. We look at fundamental theory. We try and model what is happening based on our understanding of that theory. We build a lot of instrumentation to try and observe both our own planet Earth, but also other planets and the space environment. And we do an awful lot of data analysis, often with very high-powered computing and with advanced data analysis tools. So I hope that's moved the slide. If it hasn't, let's try and move it from here. There we go. So in terms of our size, we're one of the bigger groups in the department. We have a lot of PhD students at the moment, over 30, 37 research staff and support staff, and one more member of academic staff than Ben mentioned earlier. So I think we must have had a new recruitment. So we now have 16 permanent academic staff, and 2 of our members are fellows of the Royal Society, which is fairly prestigious and shows that the group is held in high regard internationally. This little schematic shows how the group fits together. So we have part of the group working on space and planetary physics. There's a little bit of overlap with the other half of the group, which is mostly working on atmospheric and oceanic physics. And then we have a smaller part of the group that is looking at spectroscopy, both measuring spectra that we see in space and on the Earth, but also within the lab. And what I've tried to do in the little bubbles that you can see around the outside is show some of the interactions that we have with external partners, both across college, but also completely externally to Imperial. Two big ones that we have there are Imperial Space Lab, which connects activities going on related to space across the whole of Imperial College. So it brings together all the different faculties, medicine, engineering, and natural sciences. And for the atmospheric and oceanic physics side, the Grantham Institute for Climate Change and the Environment plays a very important role for us, connecting what is going on across college in those different faculties, but also looking externally to influencing things at the policy level. We also have very strong links with the Met Office, with various different space agencies, with different national and international meteorology labs, so that's particularly NPL. Someone asked earlier about connections with Rutherford Appleton Lab, and actually I have a studentship at the moment, which is in collaboration with them, and we do that fairly often. And we also work relatively closely on the spectroscopy side with the astrophysics group, as Alan mentioned earlier on. So just breaking up our sections a little bit and going through things very quickly, these are our main areas for space physics. We're very interested in space plasma, so we work, there is some joint work also with the plasma physics group, particularly looking at space weather and the impacts of the solar wind on our Earth environment, but also trying to understand the physics of the sun and our heliospheric physics and how that influences the production and the creation of the solar wind. We are also interested in planetary physics, so looking at the atmospheres and environments of other planets and the planet moons. And we have a very, very strong role in space missions and design instrumentation, and particularly in the area of magnetometry. So this is looking at trying to measure the magnetic field of the plasma and the planets. And in the top right figure here, you can see a schematic of magnetosphere and magnetopause for a particular planet. And in the bottom two figures, you can see on the left-hand side a schematic of Solar Orbiter, which is a mission to go closer to the sun than has ever been done before and have a look at the characteristics of the solar wind. And in the bottom right is a beautiful photo of Comet 67P.
Helen, we're only seeing your first slide.
Are you? It's a pity someone didn't tell me earlier. Okay, let me see.
Actually, we're on the slide with the Venn diagram of the different.
You can see it now. You can see it now. Thank you for letting me know, Jerry. Okay, let me. Are we on that? Are we on the right slide now? Can you see?
We've still got the Venn diagram.
Oh, for goodness sake.
Are you sharing screen or sharing the application?
I'm sharing the application, so it should be fine.
It works better if you share the screen.
Okay, let me see what I might just kill it and start again. Hang on a second. Let's do that. Let's try sharing the screen. Might work. I don't think that's going to work either, so let's get rid of that. It's not very good. Let's try again. I've killed the old thing now, so let's try again. Okay, that might work better. How's that? Can you see that? Is anyone going to talk to me?
Not learning anything yet.
Okay. What can you see now?
Blank screen.
A blank screen. I can see it sharing, so that's really odd. How about that?
No, it's still blank.
For goodness sake. Okay. Let me just share the application again, and then we can go from there. Okay. I will run it as if it's in PowerPoint mode. Can you see that now? If you just look at this, if you just look at the screen, is that coming through?
Unfortunately, it's just blank.
Okay, maybe run to the next presentation and come back, because if I can't get it up, then can you run it from? Have you got it, Ben? Can you run it?
Well, yes. Let me try and open it on my computer, and let's see if it works.
Okay, because it's saying it's sharing here, but
yeah, I think it might be a some kind of bandwidth problem.
Okay, I'll stop sharing.
So I just did the wrong thing. Let's see about this. Oh, now it's the problem is it wants to open in Teams. Give me a sec. I need to download it onto my computer and then open it.
Do you think we might go to the next speaker and come back so that?
Yes, let's do that. So if you hand over to, I think Andrew is going to talk for.
Helen, I'm broadcasting. Can you see it?
I can see it now. Yes, thank you, Jerry. Thank you.
Do you want to do it this way?
Yeah, if you could pop onto not the next slide, but the one after. Sorry, Andrew. Not that one. Back a couple. It's a bit slow, I think. There we are. So that's the right one. Thank you. So I was just, apologies everyone, I was just talking you through a slide that you couldn't see, so that must have been fun for everyone. But just to quickly say, on the space side of the group, our main areas are looking at space plasma, particularly using magnetometry, looking at heliospheric physics, so understanding the sun and its behavior and how that influences the solar wind and how that affects us in our nearer environment through the phenomena of space weather. We do a little bit of work on planetary physics, not just the Earth, but also other planets, including looking at their atmospheres and things like aurora at different planets. And we do a lot of work in developing instrumentation for space missions. And in fact, we have had a continuous presence on UK space satellites since the very first launch in the 1960s. I'm going to focus a little bit on current and recent missions that we're involved in. So in the plots you can see in the bottom left-hand side is a nice artistic impression of Solar Orbiter. And that's getting closer to the sun than we've ever been before. And there'll be a PhD project on offer this year, particularly looking at data from Solar Orbiter. And then in the bottom right, you can see a beautiful photo of Comet 67P, which was part of the Rosetta mission. And we've done an awful lot of work analysing the data from that mission and getting new understanding of comets in particular and their dusty environment around comets. The big mission that we're being involved in, as well as these are coming forward, is the JUICE mission, which is going to go to Jupiter and its icy moons. Okay, if we could go forward, Jeremy. Okay, on the other side of the group, we're talking about atmospheric and oceanic physics, and we have quite a wide range of things that we look at, mostly in the context of understanding our climate. So we are interested in looking at the coupling between the atmosphere and ocean, in particular in the regions of the Gulf Stream, the Kuroshio, places like that, where you have strong dynamics and eddies and small scale variation in oceanic behavior and how that couples to the atmosphere, and also how the atmosphere couples back to the ocean. Very interested in measuring what's happening in terms of the total energy leaving the planet and coming into the planet via the Earth radiation budget, both the total amount in terms of integrating across the spectrum, but also looking at the spectrum variation of that, so it's variation with wavelengths. There's a body of work within the group looking at understanding the carbon cycle, both in the ocean, in vegetation, and also how that couples with the amount of carbon dioxide and methane in the atmosphere. We have a new stream of work looking at the role of clouds and aerosol and how they link together and influence precipitation. We have another stream of work looking at the composition of the atmosphere in general, but in particular how that's influenced by wildfire and the production of aerosol and smoke from wildfire burning. And then we have a big piece of work that looks at modelling and understanding tropical cyclones and their impact on society. If you'd like to fast forward, Joe. And then a smaller area of work is basically looking at laboratory spectroscopy with applications for astrophysics. And there'll be a project this year in that area. Thank you, Jerry. Let's move forward one. So I want to just go through what the projects are. We have 8 nominally on offer, 3 on the space physics side, and you can see the 3 areas here, and you can also see the names of the supervisors that are running those projects. And if you're interested in any of these specifically, the best thing to do is to get in contact directly with the supervisor. But I will give in the chat afterwards the generic contact for the SPAT PG coordinator. And then one project looking at laboratory spectroscopy with Juliet Pickering, which is trying to go into the lab, measure spectra of particularly important elements that can then be used to understand measurements, trying to look from, say, space telescopes like this. Forward next. And then on the atmospheric and oceanic physics side, we have 4 nominal projects on offer. You can see them all here. They span a wide variety of areas. For these projects, it's very important that you contact the supervisors very quickly, because the closing date for these projects, for most of them, will be sooner than usual. Normally, we have to get the paperwork in for at least 3 of these by the end of January. So it's important to get in contact with the supervisors as fast as you can, please. Okay, fast forward, please. There we go. I will put some details about how to get in contact. I will also put some details of the Space Physics Open Day that we're hoping to run on the 12th of January in the afternoon. So you can have a look if you're interested in any of those and get in touch. Thank you. And thank you, Jerry.
Thanks, Helen. Sorry, everybody, about our slight technical difficulties. Let's go straight to Andrew, who is for the theory group.
Okay, so can you see that?
Yes, it's not full screen. Now it's full screen.
Okay, great. Okay, so thank you for staying to the end of the meeting. So I'll just tell you a little bit about the theoretical physics group. This is a relatively recent picture of us at the top of the Blackett lab. The group has a long and distinguished history. It was founded by Abdus Salam, the 1979 Nobel Prize winner, and it's not inaccurate to say that roughly 2/3 of the standard model of particle physics was developed at Imperial. Tom Kibble, who was here for many years, was one of the co-discoverers of the Higgs mechanism, amongst many other things. And Abdus Salam, of course, got his Nobel Prize for the development of the electroweak theory. By the standards of theory groups, we're actually one of the biggest. We're about 15 faculties within the department, a smaller part, but that's large for a theory group. It's one of the largest in the UK. And and just to sort of give you some measure of the impact, by a recent study on citations of research work from high energy physics groups across the world, the group at Imperial came out as one of the highest in the world, 11th, ahead of places such as Princeton, Stanford, and Harvard, and places like that. And so just to give you an overview of the research topics, the largest part of the theory group, so the main focus is really on fundamental physics, precisely that physics that, as Jonathan mentioned earlier, is taught in the QFFF master's course. And the largest subgroup of the theory group is the string theory group, which covers many aspects of supersymmetry, supergravity, theories of brains, many aspects of which were developed at Imperial. In particular, supergravity and brains were developed in the 1980s at Imperial. And more recently, that's evolved into a lot of string theory nowadays is discussions about ADS-CFT correspondence and holography. And that's the idea that theories of gravity could actually be equivalent to non-gravitational theories in lower dimensions. So, for example, a 4-dimensional universe, gravitational theory may be equivalent to some 3-dimensional theory at the boundary of space. And many other aspects of string theory are covered, such as more mathematical aspects to do with the geometry of Calabi-Yau manifolds. I also mentioned brain physics, and there's also connections into condensed matter physics through holography and connections into integrable systems. In addition, the second main part of the group is focused on more cosmology and gravity, and nowadays effective field theories of gravity. And so there's many links of that. Some of those links are into the Astro group. Some of the cosmology group are quite closely connected with data. So, for example, we have people who work involved in CMB experiments and now gravitational wave experiments, or at least on the analysis of gravity wave and for future experiments. And gravitational physics will be a big thing going forward because of the recent discoveries of gravitational waves. And on the theory side, we also have people working on the development of theories of gravity as an extension to Einstein's theory and understanding how gravitational theories fit into high energy physics. And then also we have people working on the physics of black holes at the level of modeling them numerically or calculating corrections to black hole physics from other such things, as well as more traditional cosmology. Many of us have worked on theories of inflation, dark matter, dark energy, and many of the more traditional early universe and late universe cosmology. And many people do have links in with the Astro group there. We also have people working on other non-string theory related approaches to quantum gravity. So in particular, causal set theory, which is more a discrete picture of space and time and how quantum gravity is realized at the Planck scale, as well as foundational questions about quantum mechanics itself. For example, if you have to treat the entire universe in quantum mechanical terms, then there can be no collapse of the wave function because there's no one else to measure the wave function of the universe. And so there's many conceptual questions that arise when we apply quantum mechanics and we think about it cosmologically or at the level of the whole space-time geometry. And others working on more traditional aspects of quantum field theory, lattice quantum field theory and so on, but they're not also links into connecting with, say, complexity theory and networks and using the same tools, using tools from quantum field theory in the context of other areas. So much about the applying has been said by other people. In our particular group, it is very competitive. We get awarded 200 sometimes applicants for what are only a few funded places, so typically 4 or 5 students we take on each year. And so because it is so competitive, we do expect candidates to be near the top of their class, so the top 5 or 10% of their class, and everyone as well should have a master's. We have our own master's course, but we don't exclusively take PhD candidates from that master's course. We do often take candidates, but we also take from people who, for example, have done Part 3 in Cambridge, or also international students who've done similar equivalent degrees elsewhere. When you apply, we don't give PhDs with a specific project. That's not our style. It doesn't work for theory. So all we really want to know from you when you apply is what kind of area you're interested in. So, for example, are you more interested in string theory or cosmology? It helps in your application to give us some indication of which area you're interested in. Some of the stuff about scholarship has already been said. I would just say, although the deadline for applications is sort of the beginning of February, in real terms, the sooner those applications are in, the better. It will overall help increase chances, certainly with scholarship applications and so on. So just the last few comments. Supervisors within the theory group, typically every supervisor is different. Some supervisors exclusively take only one student at a time. Others are happy to have 3 or 4 students at a given time. So in principle, everybody, each year, everybody in principle would be available for taking on students, but whether they will in a given year will depend somewhat on how many other students they have and their own particular preferences. But you should regard that all supervisors, everyone, all faculty in the theory group are potentially available. And similarly, it helps us when you do apply, if you take a look at the research that individual faculty are doing and give us some indication of the kind of the faculty members that you might be interested in working with. And so just the last few comments. I think the theory group open day is on the 26th of January. And feel free to send me an email with any questions about the theory group applications, of which I am in charge. And that's it for me.
Okay, thank you, Andrew. That brings us to the close of our open day. So once again, I'd like to thank everybody who came along. And I urge you, the Teams page will remain live, so you can look in the chat to find the links to the various research groups. So please get in touch if you're at all interested and find out more details, and of course sign up for the open days. With that, I think we'll bring the session to a close. So thanks again, everybody, and hope to see you in the future. Goodbye.